wonderful. Yeah, it's so fantastic to be here, even in these kind of hard times. But here from rainy Amsterdam, to everyone here to talk to you about teaching your sensor some new tricks with machine learning. It's going to be a super interesting webinar. We'll have about 25 minutes of presentation. I'll tell you a bit about the recent developments in the silicon industry. We'll talk a bit about Eta Compute's new silicon that has come out and what that enables. Little hint, it has something to do with new tricks for your sensors. And after that, we'll actually dive into the kind of the workshop portion of this webinar. This is Eta Compute's AI Sensor. We'll be using this board to actually train 2 different models, and I'll give you a sneak peek of something that you will be able to do with this board in about a year from now. So I hope everyone's super excited, at least I am. So as Marissa said, my name is Jan Jungboom. I'm the CTO and co-founder of Edge Impulse. I have a background in the silicon industry. I worked at ARM for 3.5 years, and prior to that, I was designing mobile phones. So also connected devices, but at a very different power class. And yeah, I'm joined here today with Samir Haddad. Samir, do you want to intro yourself?
Yeah, sure. So my name is Samir Haddad. So my background is in the semiconductor industry. I've been more than 20 years doing marketing, product marketing, and strategy for semiconductor devices, and especially microcontroller, microprocessors, and AI-enabled device. So I'm with Eta Compute since 1 year, and we have exciting products that bring machine learning to the extreme edge and to places where you usually use very small microcontrollers before.
Right, thanks, Samir. Yeah, so I want to like a little sidestep here to my photo. About 3 years ago was for me the very first time that I really got this connection of where IoT and machine learning got together, which is when I was teaching at a summer school in Arusha in Tanzania as part of Data Science Africa. And we were teaching mathematics and computer science master and PhD students on what it meant to actually do data collection for the models that you train. So for these students, very often the way they did machine learning is they get a data set, and then they start experimenting on that data set and try to see if they can get the accuracy up, and then kind of leave it at that. And for us, kind of the very first, and for me, I came into that workshop as kind of the IoT specialist on behalf of ARM. And for me, very often, after I build an IoT device, it kind of stops with the data collection. Data is collected, data ships off somewhere to the cloud, and then someone else does something with this data and makes business decisions. And all of a sudden, when we were sitting in the same room, we realized that together we'd be a much more powerful team. If the data scientists know a little bit more about how hard it is to do data collection in the real world, and if the IoT developers know a little bit about what kind of data scientists like and in what resolution and what they actually want to sense, you get super powerful combinations. So the solution that we started building there was the connected cow, a little device spanning an accelerometer and a microcontroller that you could hang around the neck of a cow, and it would then analyze the movement of the cow, depending on compared to a baseline, to detect when a cow was either getting sick or when a cow was getting in heat, which is super valuable information if you're a dairy farmer in Tanzania. So super interesting, and from there, that's the start of my journey in this. Now, if you look at like a typical industrial sensor in 2020, there's very little. There's hardware-wise, they've made tremendous strides compared to where we were 10 years ago. The fact that MEMS sensors have come up, the fact that mobile phones have come up and drastically have lowered the price of really high quality sensors has given us a bunch of really amazing devices that are currently sitting in our industrial sensors. So this is an example of one made from a company in Japan. It has a vibration sensor. It can do vibrations up to 1,000 times a second in a really, really small package. That's what MEMS accelerometers can do these days. It actually has an accurate temperature sensor. Temperature sensing, even though it's kind of the IoT 101, like everyone builds, including me, one of the very first circuits that you build is a microcontroller with a temperature sensor attached to it. Actually doing that on a high resolution is really, really hard. This one does that pretty well. It's water and even explosion proof, which is absolutely fantastic. Everything is completely soldered down on this board and it can withstand an explosion. And even with new networking technologies, low power wide area networks, for example, if we have line of sight, we can even send data 10 kilometers away using 25 milliwatts of power. And on top of that, in this device, it's a processor capable of running over 20 million instructions per second. Like, truly astonishing what we have achieved. Now, unfortunately, this device is battery powered. And thus, kind of what it actually does is very limited compared to what we can do with this hardware. Like an actual typical, this sensor actually out of the box, once an hour, it sends the average motion, just the root mean squared over the accelerometer, the peak motion, and the current temperature over. So we have this amazing device, and what we actually do with it is very, very limited. There's a reason for this, of course, and that is because this device is battery powered, and in this case, the device is actually connected over a low power wide area network. We have these bandwidth and power constraints on the device. That means that we can't really do much extra. We can't send much more data. We can't send raw waveforms or advanced analytics on this device, because otherwise we're going to burn through the battery really, really quickly. And we see this a lot. Like, it's a quote from McKinsey, 99% of sensor data is discarded due to cost, bandwidth, or power constraints. And that means that lots of really interesting events that your sensors can actually sense, that your device can sense, get lost. If this is a waveform, and this is not even an hour worth of accelerometer data, it's just 10 seconds. And one of my 3 features that I collect from the sensor is the peak motion. Then literally the only point that I'm going to get from this whole wave is this point, because that was the peak motion for the device. But if I actually look at this visually, then for me, kind of one of the more interesting points is sitting here. This looks much more interesting because it's an anomaly from what the normal pattern is. Here, the peak is a little bit wider than normal. So we have these events that get lost. And also, if we need to compress data down to a single number, like the average root mean square of accelerometer data on the sensor earlier, these numbers can be incredibly misleading because lots of different, in this case, motions that we detect here on the accelerometer can compress down to the same single number. That's leading to some misleading results somewhere down the line. So here, actually captured here with a device with an accelerometer on it, here is me doing up, down, another one with me doing a circle. And these are very distinct things that I might want to detect. But if I'm only looking at the average root mean square of the accelerometer signal, I get 3.36 here, and I get 3.35 here. So compressing this data down, while we know why this is happening, it's because we have cost, bandwidth, or power constraints, leads to very misleading signals and also throws away lots of really valuable data and lots of very valuable conclusions we could draw from this data we can no longer do due to this compression rate. So for me, it feels that on-device intelligence is really the only way that we can move to higher value use cases. So a device, rather than sending, here's a compressed version of, or a compressed representation of my sensor data, it should rather say, okay, well, I've heard a vibration pattern that might lead to a fault state in a week based on historical data. It might be that the temperature varies in a way that I've never seen before. Not the temperature has gone above 25 degrees and thus an alarm is required, but rather look at historical data and see, you know, is this something that looks like something we've seen before, or that we can recover from? Or even comparing it to other machines in your factory. Like, this machine oscillates different than all the other machines in the factory. That is interesting information. And after that, these power and bandwidth constraints are a lot less in place, because now I can just say, well, it's a single byte. The temperature varies in a way that I've never seen before. This actually might be much better for your battery life, because instead of having to send every hour, because that's kind of the resolution that I need to have any idea of how my sensor is doing, the fact that the device is sending a message is already an indication that there's something interesting going on. So for me, it would be much more valuable if this device sends me a signal only when something is going on, and maybe a ping every day to ensure that the device is still alive, rather than having to burn through cycles every hour just to send me a couple of features that don't really give me any value at all. All right, so this is what we want. This is an ideal world, but how can we get there? You might have guessed based on the title of the webinar, but there's one technology that's really great at finding kind of these patterns in really messy data, and that's machine learning. So machine learning is pretty widely used outside of Internet of Things. Kind of every place where you have a large data lake with data that's kind of in an unstructured format, and where you try to find these hidden patterns in that data, kind of anything where a human can't really reason about it in Excel, that's where you apply this machine learning. But for me, when we just started in this field, and I think for lots of people on this call, machine learning is associated with large clusters of servers. And we just figured that for us, machine learning, for us, the problem with these IoT devices is they're either power or bandwidth constraints. And so these two worlds, the worlds of machine learning with clusters full of GPUs, and at the end, the world of our embedded and IoT devices that are very constrained, kind of don't seem to be able to connect. Fortunately, a couple of years ago, a new movement was kicked off, now known as TinyML. Kind of two people here at the forefront of this new field. On one end, Pete Warden, who was working at Google at the time, and Neil Tan, who was working at ARM at the time in my team. And they kind of came to the same conclusion. So for Pete, the journey was when he was just when after his company was just acquired by ARM, he was kind of going on a quest within Google to find new interesting technology. And he started talking to the team that did the OK Google keyword recognition on Android phones. And he realized that for that team to actually build an always-on keyword spotting model, they needed to run this not on the main application processor, like a Cortex-A on a mobile phone, but rather they should run this on a separate, very low power chip. In their case, a DSP. And I figured if we can run the wake word detection there, so only response to OK Google, then wake up the application processor to the rest, that is something where you can actually hit their power constraints while still delivering a really good user experience. And the OK Google team actually managed to get this whole wake words model working on billions of Android phones in 20K of RAM or something. And he was amazed by that. And at the similar time, Neil Tan kind of came to the same conclusion in my team. And they realized that, well, if we disregard the training phase, so the moment where we try to find a machine learning model that's going to fit through all this raw data that we have and find a conclusion there, but rather focus on the inferencing. So after we train the model, how can we then run it on really small, tiny devices? Or how can we make it as small as possible? Then you can run this actually on really underpowered DSPs and microcontrollers. And the way to think about that, like in kind of the first slide, I said that the industrial device that I showed is capable of running 20 million operations per second. That is kind of typical what a Cortex-M microcontroller these days can do. So these microcontrollers are really great at running mathematical functions, especially simple ones. And a machine learning model, in essence, is just a mathematical function, but with lots of parameters. And during training, finding all these parameters and fine-tuning them until you have the best approximation of your data set, that is a very heavy process. But afterwards, you have just a mathematical function. Yeah, there might be maybe 100,000 operations in that function that you might need to execute before you have the results. But that's a lot faster in this whole training phase, and something that we can actually optimize to run on really small microcontrollers or DSPs. That was the first idea. After that, we done a bunch of new optimizations. So one of the new things that was kind of discovered about 2 years back is that you can trade accuracy for speed, and then you win a lot of speed, but you lose only a tiny bit of accuracy. So this is done through quantization of neural networks, typically. So this mathematical function typically operates on 4-byte floating point numbers, which is required while you're tuning the machine learning model. Because if you have lots of parameters, you want to be able to really fine tune these parameters while you're at it. But after you've trained it, you can actually swap it out for int8s and win a lot of speed, because now you have fixed point math on much smaller numbers. So that goes a lot faster, and you lose a tiny bit of accuracy. Second, we realized that we can reduce parameters. So some of these parameters in a mathematical function actually don't contribute much to the results. So we can prune them from the network. And then last, we have hardware optimized paths. We've done matrix multiplications on these devices for many, many decades. And we can leverage that. So we can swap out these vector multiplications that we do within a neural network by something that can run, for example, in the DSP. And just go a lot faster here. And altogether, this TinyML movement's been going on for a few years now, is really about how to get machine learning models small enough to run on battery-powered microcontrollers. So it's really good at anything with messy and high-resolution sensor data. Stuff like recognizing sounds, something that is really, really hard to do if you want to program this out. It's kind of easy to say, if I hear a sound that is above 100 decibels, okay, then wake up my microcontroller. But it's a lot harder to write some code that says, well, if someone says yes, then wake up my microcontroller. Machine learning is really good at that, at finding this boundary. Similar biosignal analysis. Any data you get from yourself is already messy, like a PPG sensor, something that sits on your finger or on your wrist, which your smartwatch might use to detect your heart rate. You can get lots of other really interesting information from that. For example, the sleep stage detection or COVID onset detection. Abnormal vibration patterns. Here as well, it's really easy to write some code that says, well, if I see vibration higher than 18 meters per second, then wake up and do something. But what if there's an abnormal vibration pattern? You can get away with writing lots of threshold values, but it might be much easier. You might find much better threshold with a bit of machine learning. And this also enables a bunch of new use cases. So for me, kind of the most interesting one is sensor fusion. And sensor fusion is a place where you have kind of one machine learning model, but multiple sensors are contributing to that model. These days, if I wanna know what the temperature is in my room, I can buy a temperature sensor, which is relatively easy to detect. But there's also some stuff that is really hard to detect because there's not a single sensor that can do that. Like, is the door to my from my kitchen to my hallway, is that open or not? Maybe if I have a barometric pressure sensor and I have something that can kind of feel wind flowing by, and I have maybe a temperature sensor that can detect a little bit of like a drop, and a light sensor that sees that there's now more light in the room because the door is open. Maybe together they can actually find this machine learning model that can detect that. So super interesting new fields. We've done lots of really great optimizations as a wider ecosystem. But the guys at Eta Compute also figured, okay, well, let's actually build some silicon that is really optimized for this kind of stuff. So I want to ask Samir back and tell a bit about the ECM3532.
Yeah, sure, in fact. So yeah, the device that we're using today for this workshop is the ECM3532. So it's a device we launched in February this year, and it looks like a microcontroller, but it's not a microcontroller. It's more like a very low power AI processor. And you can look at this very top level block diagram, what it has inside. It has a Cortex-M and a DSP. So the Cortex-M does all the I would say standard processing, management of procedural software. And the DSP accelerates the AI algorithms as well as signal processing algorithm that you need when you have a sensor application, because you never have machine learning only. You always have some signal conditioning, feature extraction, signal processing. So it's important to have this combination. And what we do and what is unique to Eta Compute is our continuous voltage and frequency scaling. It's a very unique way of designing processors, and what it means is that we are able to lower the internal voltage of our device, and we are saving a ton of power by doing that. So usually standard microcontrollers, standard processor have a fixed voltage internally, and you consume a lot of power, whatever the activity. In our case, we can really modulate internally the voltage, and power consumption is a square of the voltage. So we have a tremendous impact on power consumption, plus the acceleration, which means that at the end, we have a very efficient machine learning algorithm on device. So this device is used for many type of machine learning applications. So I'm showing here on this table the kind of machine learning tasks that we can run. So we can run audio, we can run motion, we can run also vision. And if you look at the right column, the top right column, it's really what you want to look at when you're looking at machine learning for low power devices or for battery operated devices. You want to look at the energy per inference. An inference is when you do a detection or you do a classification or you get some insight from your data. So I mean you're running your machine learning algorithm once. So that's one inference. And then what you want to see is that how much energy do I consume? It means time power. And that's very important. And you can see here that in our case, we are in the range of millijoules or even less than 1 millijoule. 1 millijoule is one milliwatt for 1 second. So that's really the critical point. And with these values, which means that we can really run machine learning with battery operated devices. And so what we are going to use today is this AI sensor board, so ECM3532 AI sensor board. It's a very nice board. As Jan was showing before, he was talking about sensor fusion. That's what we wanted to do with this board. So we have the ECM3532, we have 2 microphones, we have 1 pressure and temperature sensors, we have 1 accelerometer and gyro. We have also serial flash on the board, so you can store data. When you do data acquisition, it's something that you can do with edge impulse. And then, of course, battery, Bluetooth connectivity, and we have some extension connectors if you want to add some RF or you want to add memory. And everything is programmed directly with this UART connector. So we have a small SparkFun USB to UART board here that is delivered with in the box. So you will see, Jan will show you, it's very easy to program with edge impulse. And if you want to do more, then we have also the GTEC connector here. So you can connect a J-Link, for instance, from Seger, and you can do full development, full C, C++ development.
Wonderful. All right. So yeah, let's take it.
Yeah.
Sorry. Yeah, let's actually take it for a spin. Okay, from zero to model. So everything starts here if you want to build a new model with raw data. So as Samir said, there's a bit of flash on the AI sensor, and we have a data logger application to capture data at kind of the highest resolution possible. I'd highly recommend that if you do anything in machine learning, capture data first, capture raw data. It is still surprising to me that even when I talk to companies for which data is kind of their lifeline, predictive maintenance companies, and I ask them, could you give me 30 minutes of high resolution, maybe these devices typically grab data at 1000 hertz, can you give me 30 minutes of high resolution, healthy machine sensor data? And very often that is not even the case. I think for me, like everything starts with raw data. We can always extract features from the raw data, but we can't extract raw data from features. So for the AI sensor, we built a data collection client that can do this on accelerometer data straight here and on microphone data, but it's very easy to write some code to get data from any other sensor. After that, like machine learning is not a replacement for what we've been doing in the last 30 years as an industry around on-device intelligence. It's not that for the first time you can actually look at sensor data and draw some conclusions. We have been doing that, but we just call it signal processing in the past. Now that is still very, very relevant. Like raw data can be notoriously hard to deal with and is very messy. So for us, kind of the very first step we always take after raw data is look at a good signal processing pipeline and do that first before we even go do something with machine learning, because this already can tell us if the data is going to separate well or that there's something wrong with the data. So an example of signal processing pipeline could be, well, I'm taking my raw audio signal which is kind of 32,000 features, 16 kilohertz times 16 bits, and then compress that down to 240 features in the form of an MFCC spectrogram. It could also be for vibration data, we'll show it a little bit later, as just a bunch of fast Fourier transforms over the data and then look at the spectral power density, stuff that we've already been doing for the past 20 years, but now with a bit of applied machine learning to it. So this already helps with separating my data. So here on the left is me doing 3 things with my AI sensor. One is a fist bump to one of my colleagues. The other one is moving it up and down. And the last one, I had it attached to a can of beer and I was drinking that. And if you plot the full data set, you can kind of distinguish between the 3 classes. But if I'd ask you to point at one of these bubbles, every single one of these bubbles is a 2-second window for my data set, and then tell me, what's this fist bump, up, down, or beer? It's going to be pretty hard because anything in the middle could really be either one of those 3. You can make a bit of a guess, but it's going to be really hard. Whereas after I just do a fast Fourier transform over the data and then only look at the height of the peak on the X, Y, and Z axes, so just 3 features, it's going to be a lot easier. So for us, it's also a way of actually making our life a lot easier in ML. And then step 3, letting the computers figure it out. So kind of the 3 problems that we see that people ask them where they want to apply machine learning to is either classification, so what is happening right now, anomaly detection, is the behavior that I'm seeing out of the ordinary, or forecasting, like what will happen in the future. All stuff that can be done by machine learning. Neural networks these days get all the hype, but they're not the only game in town. If you want to do classification, so you have a keyword spotting model and you want to know if it's yes, no, or nothing at all, some noise in the background. Yes, totally. Neural network is fantastic at that. But it comes at a cost, both compute cost, as well as that you're going to have a kind of a black box algorithm. We try to guide you a little bit in showing whether it's to show what is happening in the hidden layers of a neural network, but it's still hard. There's other algorithms. So for anomaly detection, I'd rather not use a neural network, but a simple clustering algorithm, and then compare data to new clusters, because it's a lot easier to explain what is happening. And that is important once you go to millions of devices in production. And then last, deploy it. So what we can do with Edge Impulse is we take the signal processing code that you generated and all the parameters, the neural networks that you have, and any anomaly detection codes. And then we can convert it into code that can run both on the Cortex-M3 and on the optimized DSP, and automatically separate that between these 2 on the Eta Compute AI Sensor. So that's the 4 steps. We'll do that in a demo actually for 2 models. So to get started after this webinar, if you haven't had the board, grab the Eta Compute AI Sensor board. It's available for $50 from DigiKey. Or if you're waiting for your AI sensor board to arrive, you can actually do this with any smartphone. So in Edge Impulse, on the Devices tab, just click Add New Device, click Smartphone. A QR code will pop up, you scan it, and then from your phone, you can collect data from the accelerometer and the microphone and really test this whole flow out and even deploy it back to your phone. So Edge Impulse, in short, we're kind of TinyML as a service. So we're founded by silicon engineers or embedded engineers rather than machine learning or people with a data science background. So we help collect data from real sensors in real time. So through our data acquisition client that is already on the AI sensor boards, we'll help you build up valuable IPR in your company and build this valuable training data set, learn things from it, both through signal processing and machine learning, test that out back on your real devices with real data flows, and then finally deploy that in the field to your actual devices. It's free for developers. Just go to edgeimpulse.com and sign up. We have really great end-to-end tutorials. So if the webinar goes a little bit too fast for you, we have fantastic end-to-end tutorials with code, videos, and demos on vibration, audio. And Samir already hinted on it a little bit in his energy diagram. We'll also soon have vision. If you have a bit of time, I'll give you a sneak peek of that on docs@edgeimpulse.com. So yeah, time for me. Let's break out of Keynote and go to the exciting part, which is our demo. I have a question though. Can you see my webcam as well as the screen at the same time, Samir?
Yeah, we can still see both. We can see you and your.
Okay. All right, that is wonderful. So I have the AI sensor boards connected through the SparkFun FTDI breakout boards to my computer. And the SparkFun board gives me a way to program the device over FTDI. It gives me a kind of insight in the device because I just have a serial port that I can connect to, and it powers the device. So the way that I connect this device to Edge Impulse is, let me make this a little bit bigger. So I connect the device, I run Edge Impulse daemon, and this runs a small serial daemon on my computer that talks serial to the device and then acts as a bridge. So after this, my device will show up in my Edge Impulse project. Under the Devices tab, Jan's AI sensor with a little green dot next to it. And this little green dot means that the device is connected to the remote management service. And that means that from the UI, I can ask the device to start sampling data for me. This is not a necessity. So data can also come from an existing data set, if you have one in your company. You can just post data directly to the ingestion API, which is an API endpoint where you just throw some data in and it will show up. Or even collect it from other devices. So, but this is a really nice and easy way of doing this in the way here. And what I want to do here is kind of build our machine learning 101 model, which is something that can distinguish between different gestures that I do with the board while it's connected here on my desk. So I have my AI sensor here. Let's actually collect some idle data first. So the device is laying on my desk. I want to capture data for 5 seconds from the accelerometer, in this case at 62 Hertz. So I'm waiting to start. Now we send the signal to the device. Now the device captures data locally, stores it on external flash, signs it so we know exactly which data was generated by which device, and sends it to Edge Impulse. So if I make this a little bit bigger, I see that this data was actually signed with a private key that was provisioned to the device. It's connected from, the data is captured from my AI sensor, and I see the raw data here. Okay, so idle, not that interesting. Let's capture a wave. So that's me waving my device. So much more interesting pattern, but as you can see, it's an accelerometer, and accelerometers are very noisy sensors. So I've done this already a little bit prior to the webinar. So we've collected data in 4 different labels. So besides wave, we also have snake, which is me doing a snake motion over my desk. And the last one is up down, which is just me doing up and down movements. And now I want to, the thing that I want to learn from this is, can we build a machine learning model that can distinguish between these 4 classes? So to do that, we go to the create impulse screen. And there's a couple of kind of steps that we want to take to go from a raw sample that we just acquired from the board to something that we can learn from. The first thing is that we want to slice our data up. In this case, in 2-second windows, because my movements are kind of maximum 2 seconds long. And it also means that when I run this code on the board, it will take 2 seconds of data, basically, that we can then run inferencing on. If I set this to too long, it will take a long time before we can run that inferencing and run that machine learning model. So then next we add a processing block. So as said, signal processing is really important because it gives us more cleaner features and much smaller models. So we have built-in blocks for things to deal with accelerometer data, things to deal with audio data. We also have some ways of just passing raw data through. So if you want to try out a deep neural network and see if that can find a correlation in your data, you can use that too. We'll have images coming and custom blocks. So if you have a sensor that we don't have a processing block for, but you know what type of signal processing algorithm works on that sensor data, maybe you have a radar, you can just plug in a custom block here and integrate that with the AI sensor and Edge Impulse. All of these blocks are also open source. So if you want to modify them, just clone the GitHub repo, and then you can add them to the custom block. So it's not a black box sitting there. So we want to do some repetitive motion here, which is in essence just a I'll show it in the UI actually. And then we want to learn something from this data. So here we want to build a classifier. We want to distinguish between these 4 different classes. And here we'll actually add a neural network as a classifier. So my spectral features block. So here's my noisy wave data that I just collected with my 2-second window applied to it. It's a pretty standard signal processing pipeline, something you probably have done before on an embedded device. First of all, I want to denoise the data, and I do that by applying a low-pass filter. High-pass filter only gives me my noise. Here at a cutoff frequency of 3 Hertz, because that's kind of the faster that I go. And then a fast Fourier transform over it. Look at the frequency domain, and then look at the spectral power density. So what we do here is we actually go from the 2 seconds of data times 62 Hertz times 360 features to only 33 per window. So that's great. So we've lowered the feature space that we have. So it's much smaller. And we're actually, you're going to see this in a little bit after the feature generation is done. We separated the data very nicely as well. So we run this data over all the data in my data set now, and then we can plot this data, all the data in my data sets, in one graph. So if I just plot the height of the peaks on the X, Y, and Z axes, I can already see that there's clusters of data. So this is a wave cluster. Here we have an up-down cluster. Here's a snake cluster, and here's an idle cluster. So naturally, not everything separates super nicely. Like here's some weird data, but it's already a lot better. And if I can visually separate this, then a machine learning model will be able to do it as well. When you're debugging, you can just click on one of these items and see, okay, well, indeed, this is a little bit weird. And that's why it maybe is a little bit in this cluster. It looks a bit more like a wave here. So an easy way of looking at your data and knowing that what you're looking at is actually right. Then I want to train a classifier. Just one, so you can show kind of our guess of how fast it's going to run. And what we're going to do here is we take the output of the signal processing step, these 33 features for every sample in my data set, and then we're going to train, and then we're going to try and find a mathematical function that best approximates mapping that raw data, those 33 features, to one of those 4 outcomes. And the number of parameters in our function is determined by the number of layers and the number of neurons that we have here. So a visual way of editing this, if you have a data scientist in your company, or you know a little bit more about neural networks, you can just switch to the expert mode and you'll get a Keras way of just describing this, or you can just edit this in IPython notebook. But it's a really nice, easy visual way of playing with these number of neurons. Now, while this is training, I have kind of a this is my model after only training for 1 epoch. So at this point, we didn't try to find this optimized mathematical formula. We just said, just initialize it randomly and then call it a day. So in that case, we perform very poorly. You know, 40% accuracy, which on real life data will probably even less. But what I want to show her is that the inferencing time, so the time that we think is going to take to run on device, is only about a millisecond. So we can fully take advantage of the DSP that's sitting in the AI sensor and offload all these operations really quickly there. And additionally, we can show some peak memory usage and the model binary size on device. And that's a nice way, because when you're, in this case, we have a pretty small model. Once you go to higher or larger models like audio or vision models, it's really important to know that you know the constraints of the silicon that you're working with. And this way we can actually make guesses, or well, not even guess, we actually approximate how fast this is going to be, the latency of the device and the memory usage and the binary size of this, of your model. So you can make an informed decision. There's never like one right answer in machine learning. So my model training is now complete, and we'll see accuracy shoot up to 99.6%. So that looks a lot better after 2 minutes of training. So let's try it out. So if my device is still connected, I can use live classification. In a similar fashion, we can collect data from the device, and then we, instead of putting it in our training data acquisition set, we ask our current machine learning model to classify this. So let me do some waving. and see how well this performs. All right, 16. So we created 16 windows from this 5 seconds of data because we used 2-second windows with 200 milliseconds overlap. And all of those were classified as wave. So that's great. And if I actually look at my spectral features, I see that my data is right here in the purple segment, very close to other wave data. So I totally believe it. So we have something that seems to work. But there's one place where neural networks perform very, very poorly, and that is on data that is never seen before. So let me just shake my device and hope it doesn't disconnect from the USB. It's always the favorite part of any demo. So here, it actually thinks it's wave again, which, we know that is not true, right? It was just me shaking my device. Now, fortunately, when I look at the data here, I see that my data is outside of any known cluster. And if that's the case, I kind of don't trust it by default, because this is data the neural network has never seen before. So we should have an override setting here. And we can do that by adding an extra learning block. In this case, one that adds a clustering algorithm and then compares new data to the known clusters. So it's an anomaly detection block. One you can actually use even without a neural network in place. But here we use it as a sanity checker. So I'll train this on 3 axes that we have here, X, Y, and Z motion. So these are all the clusters that I have learned from my data. And now when new data comes in, we can compare it to all of these clusters. When it's close to a cluster, like the wave data that I did earlier, sits nicely in a cluster, we know this is not an anomaly. But now when I go back to my classification and shake it again, we've now overridden here the neural network. We know this is so far outside of a known cluster, we don't trust it. So don't make any decisions based on this data. This data is very far outside of any known cluster. This should be an anomaly. So you see the cluster actually outside of this. So cool, we have a model that works, or at least we think it works. We can use the model testing page to test this on a large set of data. I'll skip over it for time. And then we can deploy this. We can either run this directly on the AI sensor by just compiling a binary that includes my impulse, or, and that's naturally what you want to do once you productize this, we can export this as a C++ library that gives me everything included with highly optimized mathematics, utilizing the DSP to run this as part of my own firmware. And we have here in our documentation an example on how to integrate your machine learning model as generated by Edge Impulse in any of your own products. So let me stop my binary here because we both use the serial. And take my last projects. So I have a bunch of Flash scripts. Let me run the Mac one here. So we use here the FTDI chip to flash the board. And then we can run the same inferencing on device. All right, so there we go. So to then see what is happening, I open a serial terminal here to my boards. So this is our data acquisition firmware, and I can run AT run impulse to now run this on my Eta Compute board. So we sample for 2 seconds and then we classify. So at this point, the board is laying idly on my desk. That's great. Let me do some up and down. So 100% up down. Let me do some wave. And now let me do some shaking. So there we go. So I started doing idle, then we moved to up down, then I started doing some wave. I did it a little bit differently than my model expected, so it saw a little bit of an anomaly score, and then finally I shook it, and my anomaly score shoots up as well. And this is all running in real time on this device, so we can run, in this case, 10 predictions per second, even running here on the chip. This will go even faster once we add some more optimizations. Now, this is not the only thing you can do. I'll speed it up a little bit because we need to head to Q&A. We also have examples already sitting in here for audio models, and you're already completely set to build this on your Eta Compute board. So you can, for example, run keyword spotting. So this is a set with data. You can also capture data straight from the Eta Compute AI Sensor to get new data, to get new audio data, but also scene recognition. So one of the demos that I built early on was, okay, I'm in the bathroom. When does the shower turn on? So you can make an automatic shower timer to prevent your kids from showering too long. As earlier, we also have building blocks specifically to do this. So for audio data, we leverage Mel frequency capsular coefficients to first extract some data and then build kind of a smaller version of your data set that we can leverage for machine learning. One of the cool things that we do as well is that we can help you do data set visualization. So here we have our data set of yes and no, but we can use a dimensionality reduction algorithm to give you some insight in this. So one of the cool things you can do here is, here I have all my yes data in my data set clustered together, but I see a couple of outliers here. And if I hover over this one and I click on it, every one of these starts with yes. And that's because they actually say yes. I can click on it and then click the button. But here I actually have a mislabeled no. And it really nicely stands out already because it's far from any known cluster. So a cool way. After that, you can also build neural networks. In this case, using convolutional neural networks, still running really fast on device. So once we finish with all the optimizations for the AI sensor, we expect this to run probably about 7 or 8 times per second as well on device, including this signal processing code, and deploy this straight to your AI sensor from here as well. And the last thing that is coming later this month is that we're also adding support for vision models. So once you have a camera connected to the board, you can actually collect data. Here I built, you can actually see my plant here. Here we built a small model that does plant versus lamp detection in my living room, collecting data, then training a model through transfer learning. So what we do there is we take a working machine learning or working neural network for doing computer vision, strip off the top layers, retrain that with your images. So this actually trains really fast and on relatively little data. And then have a ML model that can actually do computer vision on still images. In this case on 96 by 96 pixels, so don't expect full motion video, 1 or 2 frames per second. But still super useful in industrial automation and in detecting stuff that is happening in and around your house. So all of that is either already possible with the AI sensor or will be coming very, very soon. And you're not limited to just what we're building. So this is something cool that was built by someone in the Jimples community, not an Eta Compute silicon, but on someone else's. There's actually a artificial nose that can detect different types of booze. So here he did stuff with scotch and rum. You just hold the sensor close and it will classify what it's actually smelling. So super cool. As long as it's sensor data, that is something you can connect to your board and actually start learning from. So yeah, get started yourself. Head to edgeimpulse.com, create an account. It's free for developers. Start building your models. Eta Compute AI Sensor is completely integrated here, anywhere from data acquisition, from accelerometer or microphone, or even from any other sensor that you just connect to it. We have really nice tools and SDK integrations to capture the data, start learning something from it, and integrate it in your own design. Because this is not something that is just cool as a demo. This is super valuable for your end customer as well, and something that can actually put you to higher value use cases when deploying this. So kind of my recap here is, well, first of all, the machine learning hype is really real. Machine learning is not just something that can run on large server clusters. It's something that's actually applicable to IoT and embedded devices. Machine learning with sensors is a perfect fit. Sensors generate lots and lots of really messy data. And the only way to make sense of the data is directly at the sensor edge. And that's where machine learning really shines. So start using the remaining 99% of your sensor data. And with that, I'd like to open everything up for Q&A.
Okay, thank you, Jan. Always impressive to see what can be done with your software on our device. It's excellent. So I'm looking at the Q&A right now. Okay, so one question is, okay, so it's a question for me. I will answer that. So can we program a stacking neural network on ECM3532? And this someone did this before. So yeah, stacking neural network is something specific. It's a specific type of neural network. We did that in the past at Eta Compute. We programmed several stacking neural network on ECM3532. So it's possible. The answer is yes. What we have seen in the industry is that most customers prefer traditional machine learning algorithms that have widely used like CNN and RNN, but it's possible. So let me see another question. Okay, so somebody says bandwidth and power plays a crucial role in AI at the edge. So do you foresee any other metrics play important role in moving AI to the edge in the future? So I give this question to you again.
Additional metrics. I think one of the metrics that Samir gave earlier in like kind of millijoules per inference, I think is kind of crucial. When putting an ML algorithm on your device, it doesn't mean that you can just constantly sample either. I mean, you still have your power constraints sitting in there. My feeling is just that when we've been looking at like the power characteristics of many IoT devices, it's kind of completely determined by how often you turn the radio on. And so we don't really think of, okay, well, I have a LoRa radio and it uses 40 milliamp at 3.3 volts when I send something. I kind of look at it at how often can I send something, and that's kind of the expected power consumption here. I'm expecting something similar, kind of this kind of duty cycling of your ML algorithm to also come on board as a metric for people evaluating their ML algorithms. So how often can I actually run this on device? And I think what's cool with Eta Compute is that what we have seen while we're building the examples for the AI sensor and doing the integration on the previous generation dev board for trade show demonstrations is that the millijoule per inference is lower than what we see further in the industry. So I think in that sense, that is going to be a very important metric and something where Eta Compute plus Edge Impulse really shines.
Yeah, thank you. Yeah. So another question maybe for the both of us. Can we collect data using the AI sensor board using BLE? So we have BLE on the board. So I have to say it's not activated yet. But what do you think of that, Jan? Is it a good idea?
Yeah, absolutely. Yeah, absolutely. So yeah, I'm not sure if there's an example for the BLE sensor right now in the SDK from Eta, but what we've done is we shipped a very, very, very tiny, like 2 kilobytes of flash, I think, ingestion library, and that's kind of wraps your data in a data acquisition format that we expect, and it signs your data, so we know which device it came from. In the end, that is a binary blob, so we can deliver that over UART to your computer, and then we send it to our service, or you can just send it over BLE, for example, like a BLE UART port to a phone or a computer intermediate device, and then just deliver it. So if you have a bit of, if you have the SDK and you have a bit of experience doing some Bluetooth stuff, offloading this is trivial and can be done and should be doable pretty soon. If we're gonna, yeah, sorry.
Yes, I would add that it's in fact very simple to use our BLE on the board because you have a list of 80 commands that you can send to the BLE. It's a UART service. Okay. So it's like UART, in fact, more or less.
Okay. Well, in all fairness, like there will always be use cases that we don't think of, like how you can offload data, but we try to make it as easy as possible, having our SDKs open and being able to wrap around their BLE service, for example, to offload that should be easy.
Okay. So yeah, the question for you again, is it possible to configure custom neural network model architecture via Edge Impulse?
Yeah, so
if Keras model, for instance.
Yeah, so we give you full access to the Keras model. So there's a UI where you can kind of click together like convolutional neural networks and some transfer learning and some fully connected layers. But if you click on the three little dots on the neural network screen, you can switch to expert mode, and then you just get a Python editor and you have full control over the model. But it has to be a Keras model though. But yeah, you have full freedom in that.
Excellent. So a question, this for both of us, I would say, but more for me. Can you give more detail how the DSP is used to accelerate machine learning? So maybe I give my answer first, and then Jan, you can add something. Yeah, so what we have analyzed is that machine learning algorithms, as you know, is mainly made of multiply accumulate. So it's a matrix multiply. That's the most I would say demanding operation in the machine learning algorithms, and our DSP is very fast at doing multiply accumulate. In fact, it can do 2 max in 1 cycle. So just that, in fact, we measure that we have a 4 to 5 time improvement compared, for instance, a Cortex M4 or Cortex M7 machine learning capability. Cool. On your side, Jan?
Yeah, so one of the things that we did early on is that, so for us, kind of like the actual machine learning algorithm is only a small part of kind of your whole pipeline, right? So it's also the signal processing step and maybe other classic ML algorithms. So what we did early on, even before we partnered with Eta, is that in our inferencing SDK, we abstracted this away. So we have kind of a pluggable way of plugging in DSP architectures. So we do this on Cortex M4 and up by plugging in CMSys DSP, utilizing the vector extensions on there. But we can also leverage external DSPs, or when Eta Compute internal DSP on the chip relatively easily. So we have stuff like, okay, we're going to do a matrix multiply, replace this by this command that way. So it's easy for us to split this up. And then additional for something we will be doing later this summer is, because there's a 16-bit DSP in, we'll do automatic quantization of some of our signal processing pipelines, like for audio, speeding this up even more.
Okay, very good. Okay, so now a question for you, or maybe for Zach, your co-founder. What is Edge Impulse monetization scheme? So wait, now somebody wants to speak about money.
Yeah, so Edge Impulse is free for developers, and will be that at least for a very long time. And we have enterprise customers that we help help organize data, make the data available in their whole company, and then running really large-scale transformations on those. So these are customers that have terabytes worth of labeled data, and they want to make sense of that. Or if you want to work with a larger team on machine learning projects, then we have an enterprise version that we can license. But for individual developers or small teams, it's free. Very good.
And maybe last question, because we are to the end of the time. So we're going to, by the way, we are going, the questions that are remaining, we are going to answer them later on our post or by email directly.
Yep.
So don't worry, you will have your answers, but I'm going to just take the last question. So last question is for both of us again. What is the camera you are using with AI sensor? So I want to clarify, the AI sensor right now, this board does not have a camera, but we have lots of, I would say, demos and software for image classification and image algorithms. And we are, in fact, indeed planning a similar board like this AI sensor with a camera. This will come later in this year.
Correct. Yeah, I don't have anything to add there.
Yeah, and on your side, Jan, what can you do with camera? So you hinted a little about cameras, but can you elaborate a little more about that?
We're starting with doing classification of a few classes, but on microcontroller devices. So you'll be able to do still image inferencing a few times per second on selected microcontrollers. And yeah, it's super cool. We're pulling it all together now for a release later this summer, and it's looking absolutely fantastic. It's amazing that because we're using transfer learning heavily on MobileNet v2 models right now, so you kind of choose the model architecture depending on the capabilities of your device. we can actually retrain this with relatively little data and get very good performing models even in the real world from that. So this is going to be super exciting. And for me, vision is one of, not but it's one of the killer use cases, I think, for TinyML, because all of a sudden your battery powered devices can really see what is happening in the real world, which is like absolutely amazing. This is something I wanted 5 years ago. And it's absolutely fantastic that we can now start making this happen, even on battery powered devices. So.
Yeah, very good. Yeah, and definitely we can do vision with Eta Compute silicons. No problem.
Yep. All right.
Okay, so I think we are good. Thank you everyone for attending. We are going to post the recording of this webcast online soon. And again, thank you everyone. Thank you, Jan. And we'll answer all the questions we could not answer today directly, either by email or by posting on our blog.
Yeah. And I wanna give one final note, and that is, for me, I started programming when I was 11, and the very first time that I in Visual Basic, I had like a little text box, and it says like type your name, and I said Jan, and then my computer said back hello Jan. Like that is such an amazing feeling, and that is the feeling that I got when I got my first machine learning model running and actually responding to stuff that I was doing in the physical world. So if you haven't tried it, like really pick up a board and start doing this, because this is absolutely amazing what you can do here. So thanks a lot, and we'll let me know if you want to be in touch.
Okay, thank you everyone.
Thanks, Mir.
All right, thank you everyone for joining. You will be getting an email tomorrow with the link as to where the video is going to be posted on our YouTube page. And that will also include the slides that Jan is referring to. And if you have any questions, we will be emailing you independently. So other than that, if you have any other questions, feel free to email me at Marissa at Eta Compute, or I can also forward the information to Samir and John. And other than that, that is all we have for today's webinar. All right, have a good day, everyone.